Can you hear me? And am I on the stream? Okay, good. So yeah, this session is in many ways taking more of a step back from the previous session. So this is even in some ways even more basic than talking about like the natural numbers that we saw in the previous session. Because this is about to introduce you to more thoroughly to the basic logical connectives that we have to use in Lean in everyday life, and especially when the audience consists of mathematicians, this is sometimes even more awkward to talk about than if most listeners are computer scientists, because talking about logical connectives is something that most mathematicians don't really think about them because they take them for granted. And most mathematical fields are not really concerned with any foundational issues that might have an effect on how logical connectives work or don't work in certain settings. And in Lean, this is especially it's in some places especially complicated because Lean at its heart is based on a constructive logic, but MathLib and the entire ecosystem of math formalizations assumes that we work in a classical logic, like the one that you're probably used to from your work in mathematics. And basically what we will do is we will go through all of the logical connectives and give you a few examples on how to use them. And then there's a few exercises. They're at the bottom of this file, which I will check into the repository after the talk. And then there's also more exercises in the files from the Mathematics in Lean curriculum, which you can also do if you're not yet, if those are too easy that I put on this sheet. Okay, so let's take an overview on the most important logical connectives. So we will start by looking at the implication and the universal quantification, and then talk about existential quantification, about negation, conjunction, disjunction, and I think we will leave out by implication because it's nothing new if you've seen the other ones. And I provided you with a little cheat sheet on how to use all of the logical connectives. And in the left column, you see the connective, and in the middle column, you see what you can do with them if they appear in a hypothesis H. If they appear in your proof context. Just to repeat, if you're inside a theorem and you have this info view open, the stuff before the turnstile is your context. It's a context of local hypothesis and local variables. And the stuff after the turnstile symbol is your goal. And maybe it's good to have this open as a cheat sheet, so to say, if you don't remember how to use the logical connectives. And they all differ in terms of what to do with them if you have a hypothesis and you want to deconstruct this logical connective, or if you want to prove the logical connective, which would be the rightmost column here. I will now go through all of these in more detail. There's by contra for proofs or contradiction, and also these logical connectives don't actually have to be displayed in your context, but sometimes they're also hidden under other definitions which you can unfold. But for example, like you've seen in the previous talk with the definition of the singleton set, which in the end was just an inequality. You can, for example, you will have an existentially quantified formula at the heart of the definition of A divides B for natural numbers, because it basically says, okay, there exists a K such that A times K equals B. So this is actually an existential formula. Or if you have subsets of a certain type, S and T, and you have that S is a subset of T, then that's actually a universal quantification, because because it's, we will see. You will see later, because the next session will be about sets and functions, if I remember correctly. So subsets will be probably introduced in the next session. Okay, let's start with the first logical connective, and we bunched two of them together because they're basically the same in Lean. And those two connectives are implication and universal quantification. And you've already seen in the first session the type of functions between two types, A and B. And implication and universal quantification in Lean are just examples of functions. So instead of having, having a function from a set A to a set B, an implication is just something that takes a proof of a statement A and returns a proof of a statement B. And likewise, a universal quantifier, a proof for a universal quantification is just something that takes an element of the domain of the universal quantification and returns a proof that a certain property holds at this point of the domain. And so let's take an example theorem. Okay, let's take 4 real numbers and 2 hypotheses. So let's say that x is less or equal than y, and z is less or equal to w. And then we want to have that x plus z is less or equal than y plus w. And basically, this is just like wrapping around the lemma that's already in the standard library. And now we open a section where we say, okay, let's fix some variables in the reals, and let's fix 2 names for these hypotheses. And now we can check the type of this theorem, and then you will see that it's basically displayed in the same way as above. But if we add an @ symbol, which basically it just changes the way the function takes arguments, and in this case it just changes the way it's displayed here. But here you can see that what were just usual binders in brackets up here, like the x and the y and the z and the w and the 2 hypotheses, get already displayed as implications and as universal quantifications. So what you do when you write down a theorem like this with arguments and brackets is already building a universally quantified formula or an implication. What we can do now is we can step by step supply more arguments to this function. We can apply the A and the B, and then they see, okay, now it's still a universal quantification, but it only now depends on two variables as opposed to 4 variables as before. And if we now also apply the C and the D and the H1, then we see that it's a simple implication, because now we've supplied so many of its arguments that the universal quantification vanishes, and it's just an implication. And if you look close enough, you'd see that the type of H1 and H2 is such that actually there's nothing else we could put in the first 4 arguments to my add Lee add, because the H1 and the H2 already determine the exact value of the first 4 arguments. And this is a quirk, a feature of dependent types, the basis of Lean. And in such situations, we can do one thing. We can basically add like a zebra crossing of underscores, which are just placeholders for the names, if we don't want to specify the A, the B, the C, and the D every time we want to call this function. But obviously, this doesn't scale. If we have a function that takes 16 arguments, we don't want to sit there and type down 16 underscores. But instead, what we can do is what I did here with the my add lee add prime is that we change some of the arguments to so-called implicit arguments. So you see the difference between this and this is just that instead of having round brackets around the x, y, z, and w, in this case we have curly brackets. And curly brackets mean that these arguments are implicit, so they don't have to be given explicitly when we call that function. So if we now check our new function, we don't have to give the a and the b and the c and the d explicitly anymore. And if we want to make every argument explicit again, there's one way to do this, and this is just adding the add symbol, and then we need to provide that zebra crossing of underscores again. But so yeah, these implicit arguments are there, later arguments of the function. So yeah, that's an important feature of universal quantification if you don't want to give every argument all the time. And now one running example in this file will be functions that have an upper bound, functions from the reals to the reals. And so we can, for example, define what it means for a function f to have an upper bound a. We can just say, okay, yeah, for every x, f of x should be less or equal than a. And we see that we don't have to actually specify that this should be an x from the reals, because this part here will be inferred by Lean, because we put it into f, so of course it has to be a real number. Also, we don't have to specify that this is a proposition, because this will also be inferred by Lean, because it's a universally quantified formula, so it should be a proposition. Yes. So we could also have an underscore here, or just an a. Does that work? Yeah. It's not, I think at this point it's not good style, but it's possible. Okay, so let's prove, oops, sorry for everyone on the stream. Let's prove a basic property about upper bounds. Let's prove that if we have a function f that has an upper bound a and a function g that has an upper bound b, that the function f plus g has the upper bound a plus b. Okay, so this is what our proof context looks like. Okay, what to do? At first, it might be a good idea to get the quantifiers that are lingering around here out of the definitions that hide them. And we can do that, for example, by saying simp only, and then we want to unfold the definition. And so now we've only unfolded it in the goal. And one way to also unfold it in the hypothesis is to say add star. And then we've unfolded it everywhere. We could also be explicit about the positions where it should be unfolded and say it should be unfolded at FHA, it should be unfolded at HGB. So that's the name of the hypothesis. And at goal, it's just / goal to write this goal symbol. And yeah, now we've unfolded it everywhere. Okay, so now we have a universally quantified goal. So what do we do with it? We said, okay, for every x, something should hold. And the tactic to introduce a new variable, which is what we should do here, we should say, okay, let's fix an arbitrary x. And we do that with intro x. Okay, now the x has moved from the goal into the context. And now what we see is that f plus g, we have f plus g of x on the left-hand side. And this should be simplified to f of x plus g of x. And we can do the same thing that we saw in the previous lecture. We can do simp, and so we've expanded this. Okay, so now we have we have these assumptions which are now more general than the thing that we actually need, because we actually need those only at x. And one way to do this is, okay, let's have another hypothesis. Let's call it HFA prime. And we say that this is the HFA applied at x. Okay, now we have like the more concrete hypothesis. So this is one way. The other way would be to use the specialized tactic, which just says, okay, this hypothesis is too general. We want to specialize it. And you see that both of these ways have certain advantages and drawbacks. Here, if we do it with have, we still have the old, more general version lying around, and if we do it with specialize, it already automatically removes the old version. So in this case, specialized would probably be better because we don't need the more general version anymore. How do we continue? We can, for example, just do linear if, because at this point it's just a bunch of a bunch of inequalities about the real numbers, and linear if is a tactic that does linear arithmetic, and in these cases that works fine. I wanted to show you something about proof structuring here, but I don't remember what. Okay, let's move on to the existential quantifier. Okay, first example. We want to prove that there's a real number that's larger than 2 and smaller than 3. And so if we have an existential quantifier in our goal, one of the ways is to just use the use tactic, which basically just says, okay, to give this, just use, say, 2.4. And this now plugs in the corresponding value into the existential quantifier. So yeah. And at this point, now we have to prove these two things. But as we saw earlier, if there's really only numerals involved in the proof goal, norm num will always do the job because it's basically Lean's calculator. And as I said, there's sometimes there's existential quantifiers hidden in other definitions. We could try to click our way. We would have to use the synth command to actually get to the definition of the divides here. But since we might know it's an existentially quantified formula, we can also use the use tactic here. And so, okay, what number do we need here? We can use 4, and then we're already done, because use already, it uses trivial. It uses a tactic to close trivial goals after plugging in the value. So yeah. Okay, and so another example that basically connects to the example that we have had earlier is that, okay, now we've defined what it means for a value to be an upper bound for a function. So imagine we now wanted to define what it means for a function to have an upper bound, to have any upper bound. Then we would need an existential quantifier here. It says, okay, there exists an A such that A is an upper bound for F. And now, also connecting to the earlier example, now we can prove that if F and G both have an upper bound, then F plus G have an upper bound as well. And again, we can do simp only fn has ub at star, to unfold the definition. We don't have to do this in this case, but it's maybe just good for visualization. Okay, now we have UBF and UBG. They're both hypotheses that state the existence of this upper bound. And how do we decompose those? There's basically two ways, and I think Rcases is the cleaner way, because it's a very nice tactic that allows you to decompose almost any variable in your context. So let's say Rcases UBF with A and HA. So we usually call, if we have hypotheses that are some statement on a variable A, it's usually the common style to call them HA, for example, just as a name for the hypothesis, just so that we know what the hypothesis is on. And now we've basically decomposed. So this was the state before, and now we've decomposed this UBF hypothesis into the witness and the statement itself. And now we can do the same. UBG with, now we have to give it another name, B and HB. Oh, and yeah, it's important to note that these are like these angled brackets, and they can be inputted with the backslash and then the less or greater than signs. Okay, now we've inputted, we've decomposed both of the hypotheses. So we have this A and we have the B in the context. And so we want to prove this existential quantifier, so we can use the use tactic again. And who can guess what we should put here? Yeah, exactly, A plus B. And now this looks like an application of the lemma that we've proven beforehand. So we can just say apply, or we can let's use exact here, exact, and then we need to provide the HA and the HB, and then we're done. Okay, so now we've proven that F plus G has an upper bound if F and G both have an upper bound. And we can also do stuff, then we can later clean up the proof if we want, and for example, say that, okay, this simplification, this unfolding of definitions wasn't really necessary, and we can delete that, for example, to make it a bit shorter if we want. Yeah. What's the use of the Rcases? What does it do? So if you have a hypothesis that's, so it's a more general tactic, but if you have any composite hypothesis, for example, something that's an existentially quantified formula, something that's a disjunction, which we'll see later, you can decompose it. So well, let me add this again. So whenever you'll see something that you think, okay, this is composed of several things, you can take it apart with Rcases. And we will probably hear in a later session about inductive types and about structures, at least about structures as well. So these tactics work on a whole variety of different types. But for now, it's enough to know that they work on almost any logical connective, except for universal quantification and implication, because we know that those are actually functions in Lean. And then there's one little caveat when it comes down to existential quantifiers. So we could use Rcases here just because the thing we wanted to show was actually a proposition. But assume for a minute that instead of wanting to prove a statement, we actually wanted to construct a natural number. So we had like a hypothesis for whatever reason. We had a hypothesis that there exists a natural number, that's larger than that's bigger than 4, and we wanted to construct some natural number. And we wanted to try, okay, let's do Rcases h with x and hx. And then it says, okay, it gives us an error message. And that's because Lean is built on a constructive logic that assumes that every function that we write will be computable. And that's why we can't deconstruct existential quantifiers, for example, in a setting where we're not about to prove a theorem, but instead we're about to construct some piece of data. And there exists a way around that, which is exists.choose. It's a variant of the axiom of choice in a type theoretic setting instead of a set theoretic setting. And what exists.choose gives us is basically for every existentially quantified formula, it gives us some element of its domain, and then we have another theorem that is called exists.choose_spec, which says that this thing that we've chosen with exists.choose actually fulfills the property that we wanted to fulfill. And so yeah, one way to get this here is to say, okay, this should be exact. Okay, now we've gotten rid of this one error message, and now we got a different error message because it says, okay, this you've created a definition, but we will not be able to produce any executable code from it, and so we will have to mark this as non-computable. You can also mark entire files with non-computable, and for Mathlib, there's huge portions of Mathlib are actually non-computable, even if in theory they could be formalized in a computable way. But one of the principles when Mathlib was started was that we should focus rather on the growth of the library than on making sure that everything that is computable is formalized in a computable way. Yeah, but in some ways, the downside to formalizing things in a non-computable way is that if we then use the eval command that we've seen earlier, so let's use the eval command of 5 num. So this should be like a valid call to choose nat, because this is basically just giving it the number and the proof by norm num that the number 5 is greater than 4. But it says, okay, it can't evaluate that function. So we can write functions in Lean that are not evaluable with the Lean compiler. So that's a caveat of the existential quantifier that one needs to be aware of, and it might become relevant in the later sections, probably not that quickly. Okay, let's come to the next logical connective, which is negation. And negation is also a function type. Negation in Lean is just defined as A implies, so not A is just implemented as A implies false. So if you think about it, it makes sense. It just says, okay, if we can prove not A, if we want to show that not A holds, then we can assume A and show a contradiction. That's basically what it says. Okay, so let's see. We have for all A, there exists an x such that f of x is greater than A, and we want to show that our function does then not have an upper bound. Okay, let's first again unfold this, and then we see that the outermost connective here is the not. And because the not is just a function or just an implication, we can just say intro, say h prime. And now we have to prove false and have as a hypothesis this existential. And now we can say Rcases, h prime with a and ha. So now we've dissected this. And then there's whenever you have an intro and an Rcases, you can also combine these two. And you could just say R intro. And then just give the structure directly. So that's just if you want to save space. Whenever you want to intro a new variable and you immediately know that you want to take it apart, you can just use R intro. But you could also use intro and then do Rcases and deconstruct it. Okay, now we know that A is an upper bound of F, but we also know that for every A, there exists an X that takes a bigger value. So we want to specialize H at the point A. So now we can also do Rcases H with B, HB. So sometimes when I'm doing these kinds of very easy proofs, I'm kind of switching off my brain and just do the only thing that Lean allows me to do. Let's also okay, now we can also see here that this is for arbitrary X, but we also only want to know it for the B. So we want to specialize. We want to specialize H, A, and B. Yeah, at this point it's again linearith because we now have both contradicting statements. If we wanted to do it, yeah, in a manual kind of way, we could say, okay, we want to from the less or equals here. We can rewrite this at HB. Is this not? Not LE. Ah, not LE, thanks. Oh no, I think it's because you use greater than. Not GT. Do we have this? Maybe not LT at HA. Sorry, again? Not LT at HA. Oh yes, that's it. And I think now we should be able to say contradiction, which just says, okay, there's two directly contradicting goals, directly contradicting hypotheses in the context, and we can prove false from this. We could also do away with all of this and use asop, for example. That's a tactic that automatically searches for goals. So let's comment this out for a while, and I'll show you just another way of proving the same thing. Let's say, okay, let's unfold Fn has UB and unfold Fn UB, and then say asop, then it does that by itself. So asop is basically a tree. Okay, in this case, it's not a very broad tree it has to search, but asop is a tree-based proof search tactic that does a very intelligent heuristical way of searching for proofs, not in a depth first way, not in a breadth first way, but in what it calls a best first way. You can basically say, okay, this proof step is a safe proof step, so it should always be applied when it's possible. And this proof step is very unsafe, so it only will lead to a success rate of, I don't know, 30%. And then asop will try to find the best way to approve. And there's also an asop question mark, which will just a simp question mark will just give you the proof. In this case, probably also like just simp question mark is also enough to. Oh no, not yet. Not yet. Should also be an assumption. Yeah. But yeah, so that you've seen. If I can show you ways to deal with all these connectives in a very manual way. But in the end, the more automation you use, the more you will not have to deal with the details of these. Yeah, especially asop is a very mighty tool, and I guess you will see it used much more in MathLib in the coming years. And
what is actually the tree that this searches for?
So in this case, we don't really have a tree, but if we had like a disjunction as a hypothesis, it would do like the case distinction: is the left hand side true, or is the right hand side true? Whenever there's an if statement in the context, so if this proposition holds, then f of x equals this, otherwise it equals that, then we'll do a case distinction on both of these things. Whenever it could also do a case distinction on the natural numbers, whether it's a 0 or a successor natural number, and so on. And you can imagine that these trees grow very quickly before it finds a proof. So the tactic can be quite slow. But in easy cases like this, it's actually, it starts calculating when I write down the p, and it's actually pretty quickly. Yeah, if we add more simp lemmas, for example, changing the set of simp lemmas will change the way the tree search works, because the simp tactic is basically a part of the asop tactic. Yeah, so in general, I'd say it's bad style if for simp and for asop if you use it in the middle of a proof. If you use it at the end of a proof, it's not bad style, because I think the worst thing that can happen with simp, nobody will put something that causes loops inside simp, because we assume that people act responsibly. But what could happen is that simp just becomes stronger, and then the proof state after calling simp in a proof, it could just be like that you just further down the proof just by calling simp, because simp became stronger and did more than you expected, and then the rest of your proof breaks. And that's why it's acceptable to have simp or asop as a terminal tactic in a block of tactic calls, but not as an intermediate tactic. Okay.
Sorry, can I ask? So this asop without the simp in front, it would not have worked in this case.
Yes, because it doesn't unfold things. Yeah. There's a way to add. There's a way to add options to asop. You have to read you have to read the documentations, but you can add arbitrary rules to asop and modify it. And for each call, say, okay, give a weight of like 80% to this kind of stuff. So there's no limit on how you can basically modify the tree search. Yeah, so much for that. Okay, let's just. Yeah, this is a use case for a tactic called push neg, which which pushes negations to as much inside of a term as it can. So let's again unfold. So we've unfolded both of the definitions that we made. Now we've seen that we have the negation at the very outermost part of the formula, but we know that there's logical tautologies that, at least in classical logic, allow us to push the negation outwards and inwards. And push neg is just a tactic that does nothing more than pushing it inside. And in this case, this basically just completes the proof. Yeah. Yeah, so push neg basically goes from the outside and tries to push the negation as inwards as possible. And apparently it also does why does it do that? Yeah, and apparently it also, what it also does apparently is that it changes from not fx less or equals a to a is less than f of x. Do we know why does it do any simplification? Or?
I think it's just special case for
yeah, maybe it's, yeah. But yeah, it's a very useful tactic if your negations are too far outside. Okay, I'll speed up a little bit. Conjunction basically behaves pretty much the same as the existential quantifier. The reason for that is because it's also an inductive type. But okay, one way where it actually differs is that if you have it in a goal, so your goal consists of a conjunction of two statements. One way to say, okay, I want to construct this is to say constructor. And now we have two goals. I think this is the first time in this week we've seen that we can have more than just one proof goal. And what we do in the case where we have several proof goals is that we want to structure the proof. And the best way to structure proofs is to have these little dots, which we can type with \dot. Yeah, which just create sub blocks of tactic sequences. And so, okay, first goal is just an assumption. And the second goal, I can just use linearith to. I mean, you could also do this like manually. This is a consequence of the irreflexivity. So I think the lemma would be called do asop with the question mark, and then it gives you, for example, it gives you a bunch of. That's not very nice though. Okay, I just use linearith. So yeah, always keep in mind to structure your proofs as soon as you are in the situation like this where there's multiple proof goals, because otherwise you will basically, if you just have one big spaghetti code block of linear tactics, you pretty much get lost in, okay, where does this goal actually come from? How many goals are there still left? So structuring your proofs is really important.
Is this only for scoping, or is it also for restricting to which case it applies?
So this actually does two things. It focuses on one tactic, on one goal. So it basically goes into a state where there's no other goals. And if I don't do anything, like, okay, skip is the tactic that doesn't do anything, then it will display the error at the correct point.
So for the first step, it would focus on the goal left, on the left.
Yeah. Yeah, I think we'll see more. Also, we'll see more structured ways of doing this when we come to the topic of structures later on. And what can we do if we have a conjunction in our hypothesis? we can do Rcases. Just as I said, Rcases can decompose all sorts of hypotheses. So we can say Rcases H with H1 and H2. And then we have both of these. We can say linearith. No. Say intro H3. No? Okay, let's. Okay, yeah, that's also a way. I wanted to use the like a lemma, but yeah, apply. Oh, that's actually a good idea, because now we've seen that we have this non-equal sign, which behind the scenes is a negation, which again behind the scenes is a function which maps into false. So we can do apply H2. No, okay, and do you know what it's called? Ah, right. Okay. Okay. Yeah. So yeah, in this case, I'd have to guess. I had to guess what the name of this was. So it's the anti-symmetry of the order relation. If I didn't want to decompose this, instead of doing this, I could have also, instead of having here H2, you could also use H.2 and H.1 without actually decomposing the hypothesis with an extra tactic step. The only caveat with that is that if you have more than 2 components, then the leftmost one, say you have 3 components, then the leftmost one is called H.1, the next one is called H.2.1, and the third one is called H.2.2, because behind the scenes structures or any sort of structure with more than 2 fields get basically converted into like a sequence of. So that's not so nice when using these dot notations, these .1 and .2 notations.
This is a structure with fields repeated multiple times.
Sorry?
If you have a structure with 3 fields, they are called 1, 2, and 3. But this is a structure with 2 fields, where the second field is nested here.
Oh,
there's 2 1 notations.
Does .3 work now?
It always did, but it doesn't work now.
Oh, okay. Okay, yeah. Yeah, true.
Intros, or how would H3 become this particular inequality?
So this is an abbreviation for if this holds, then false. I can also what this is called. This is called big knot. Yeah. So if I unfolded the definition of the knot, that would be this, and then it's basically an implication. It's an implication says that if y is less or equal than x, then false. And so I can use intro to introduce the domain of that, or the left-hand side of that implication, and then we are in this situation.
Can you also explain this anti-sim? So how is it something?
Oh, that's so. There's this dot notation is there for. Yeah, we've seen namespaces in the first session, and if your namespace coincides with the, I hope I'm explaining this right. If the namespace lemma is in coincides with the name of the type, then you can basically use this dot notation, because H.1 is a less or equals. And so the name of this lemma is actually le.entersim. And because that I could also write.
So it's not a prop, this inequality, it's something else.
Yeah, it is a prop.
Okay.
But so the H1 is not the prop, but it's a proof for the less or equals. I mean, it's not okay. It's not really relevant. I maybe should have written it in this way straight away. But just this dot notation in many cases allows you to have things shorter by. I guess it's more intuitive to first introduce it in examples where, I don't know, instead of a proposition here, we'd have like a group and then say group dot characteristic as g dot characteristic or something like that. Or I will see tons of examples in the coming sessions. Okay. Last but not least, let's do a little example on disjunctions. Namely the lemma that if x is less than the absolute value of y, then s is less than y, or x is less than minus y. So we can do intro h to give it a name. Oh, by the way, I'm not sure if you've noticed, but if sometimes I'm in a situation where I haven't given enough names to a tactic, then we get these gravestone crosses in our context. And these just say that these variables don't have any accessible name. Lean is very strict about only being able to name variables that we've given an explicit name. So whenever we could just write intro and it has the same effect, but it hasn't given a name to the hypothesis that we've introduced. And so there's no way to actually there's no good way to actually access this hypothesis. We could still use a tactic like assumption where we would just refer to any hypothesis, but it's always better to give it a name. But yeah, just in case you were wondering what these crosses in the context were meaning. So what do we do here? We could, for example, say we want to prove this by cases. By cases of whether y is less than 0. By cases is a tactic that just makes a case distinction on any statement and calls the resulting hypothesis with the name that's before the colon. So we have now two goals. One where we are in the world where y is less than 0, and one where we are in the world where y is not less than 0. So we can do some proof structuring again. I always do the structure first and fill it with sorries and then try to fill in the sub-goals. And now we can, okay, we can now, we want to now simplify the statement h. So we could say simp at h. But for that, we want to use, no. Okay, I thought it would work, but yeah, thankfully I've written like a little cheat here. So here we have this is our lemma that we want to use. It says that if a is less than 0, then the absolute value is equal to minus a. And so we want to rewrite this applied to our hypothesis hy at h. And now we've changed this to x is less than minus y. And now what we have to do is we have to choose a side which we want to show in our disjunction. We have to show that either x is less than y or x is less than minus y. And in this case, for disjunctions, the best way to do this is to say right, because we want to prove the right side. This is a tactic which is it specific to disjunctions? Does anybody know? I've only ever used it with disjunctions.
I don't think.
Yeah, maybe it's just specific to any structure, any type of two constructors. But yeah, this is a good use case for it. We can say, okay, it's the right case, and then it's just assumption. Oh, we can also put this, just to show you something, we can also put this at the start of the block. Just to show you one thing. We had a rewrite here, where at the end of the rewrite, the hypothesis that we've rewritten was exactly the same as the goal. And there's a little shortcut. If you don't want to write assumption afterwards, you can just write RWA for rewrite and assumption, if you want to do the same thing in one step. Okay, and this is the case where we are we want to show the left case. And we want to use this. We want to rewrite not LT at HY. And now we have 0 is less or equal than y. And now we can rewrite. Now this looks better. So when we can now plug in this hypothesis to the lemma that says, okay, what does the absolute value look like in a non-negative case? Yeah, and this is again like just the assumption. So this would be finishing the proof. And oh yeah, I'm almost done. As one last step, just to show you that Rcases is actually like really, really nice if you have like nested formulas of any sort. So say we have an hypothesis which has like a conjunction inside a disjunction, and we want to do Rcases. For the disjunction, for everything that splits cases, we can do Rcases H with H1, H2. And now we get two goals. Note that these are round brackets and a pipe symbol in the middle. So this is deconstructing the outer disjunction. So we can have like first subgoal here, the solution to the second subgoal here. But now we know, okay, the stuff that came out of the first case is like a disjunction. And Rcases actually works recursively. You can nest the pattern that you give here. So you can say, okay, this is H1 and H3. I mean, these names are not perfect. And now we've basically decomposed it even further. And obviously, you can nest it as far as you want and yeah, decompose any sort of formula in that way. And then there's, for example, for this case, there's tactic called trans, which is for transitivity. which would be like a very, very explicit way of solving this. This is just assumption. Yeah. So I think that's the last bit I wanted to show you. Yeah.
So the choice whether we use the bar or a comma inside the bracket was this because it was either conjunction or disjunction?
Yeah, or more general, if it's a thing that spawns multiple goals, it's the bar and the round brackets. If it's just a decomposition that just spawns one goal, it's the angled brackets and the comma.
So wouldn't it then need to be the other way around? I mean, for the disjunction.
Well, the disjunction gives you two cases because either the left-hand side is true or the right-hand side is true.
Because it was some assumptions.
Yeah. But all of that is also in it's basically in this cheat table on the top of the file. Okay. Then thanks for listening and have fun doing the exercises. There's a bunch of exercises down here. I think they're pretty good to get started. And if you're done with those, you can find more exercises in the repository from these mathematics and lean session files.